with no visual aids. How's that sound? No. This is a code flow graph. So welcome. My name is Atlas. I have been here for, well, since the beginning of GrrCon. I love GrrCon. I even wore the t-shirt. Chris thought that I wasn't sporting enough, though, so I went for the head gasket here. A little bit about me. I've been very, very fortunate. I've had a good career path, dragged me through. I don't know. You told me to tell you when I was ready to start, whoever's recording. Is that okay? We good? All right. So a little bit about me. I got my start professionally breaking out of VMware. And then from there, breaking out into power meters and power systems. I've been doing programmatic disassembly and debugging, blurring the lines between static and dynamic analysis for about 13 years. I love, honestly, everybody has their own thing, right? What gets you up in the morning? What makes you feel like you're in your groove, doing things your way and being powerful? Most of you probably know what I'm talking about. For me, it's typically Python command line and doing everything from the Python command line. Interactive Python coding, copy and paste into a text file, you're done. So about 13 years ago, I got involved in disassembly in Python. And very quickly found great power to walk through entire paths of code, maybe make some logic reasoning about the code. But then I found emulation. So for a very large chunk of my career, that from the command line disassembly thing grew into from the command line emulation. You know, most of you, when you think of emulation, raise your hands. How many of you think of MAME or some sort of an NES emulator or something like that? No, okay. Only a couple of you? All right, there we get the truth. So this is not that. Now, I mean, it's a very powerful type of emulation, but we'll talk more about the different options here in a minute, as soon as I can show you my slides. If it works, don't fuck with it. It looks good on my side. Keep calm. It worked on my box. So what is emulation? Hand. Anyone? You're pretending to be a chip that you're not. Perfect. That's exactly where I was heading. So what is a computer system? Everything boils down to the grassroots with me, right? From photons and electrons, you know, now we're into a chip. What is a computer system? Well, it's what? Fancy. What was yours? A rock that thinks. Indeed. Wow. We'll have discussions over beer later. A computer system is what? It is a processor made up of memory, made up of special memory known as registers, some peripherals, and some ability to listen to whatever code needs to be run and to do it. Okay? So those major things. So if we're going to write an emulator, and we're not going to in here, not enough time. But no. If we're going to write an emulator, what are we going to do? We're going to fake out some sort of a memory map. We're going to write code to interpret bytes from that memory map as code. and further code to do the things to that memory map, that fake memory. It's fake memory, I love that. That would have been done by another computer system. Basically, I'm writing, in Python, by the way, another computer system. Why? Well, because it's fun. This is really a problem. So here, if I turn this around, I could. Is there an IT person in the house? Yeah, right. How many hackers does it take to break it? Just one. Just one. I'm guilty there.
We did that already. Yeah.
Okay. So why in Python? Well, because I said so. And you're here, and I'm here, so that's the answer. I love Python. It just makes me happy. Plus, I write really shitty-looking code, and Python makes it so that I at least have some formatting. So IPython is one of my closest friends. Vivisect, a binary analysis framework, is my tooling of choice for both disassembly / emulation and debugging. There's a built-in debugger cross-platform and built-in disassembly and emulation framework. Pure Python, except for the hooks into the operating system required for disassembly or for debugging. And you've probably heard me talk. If you come to my talks, you've probably heard me talk about Vivisect before. Vivisect is made up of a bunch of different components. I've talked about several of them, namely symbolics. You've probably heard me talk about symbolics before. I haven't talked too much about emulation, partly because by the time I got really good at emulation, I was onto symbolics and I thought, oh my gosh, this is the best thing since sliced bread. Turns out both are very powerful and they answer different problems. So we're going to talk about emulation today and a couple different types of emulation. The first type of emulation is real emulation. This is where I create space for an entire system or program. I can mock up a kernel in the emulator. All I need is the program. What I find myself doing a lot is mocking up an embedded computer system like those that run in cars. So I create this computer system. I start at the reset vector, and then I emulate the code within this construct, these confines of memory. And aside from peripheral access, like the things that talk to a monitor or the things that talk to a network adapter or whatever, pretty much an emulator does a great deal towards mocking up the system that I'm trying to test. And I don't have to have a running process for that thing on an architecture that's supposed to run that thing. Does that follow? For the analysis that I want to do, I don't want to have to actually go find a PowerPC chip that has the right architecture instruction module, because PowerPC, oh my gosh, it's insane. I don't want to have the thing have the right memory mapped I/O for the serial port or the CAN bus adapter. No, I don't need that. What I want to do is be able to do that on my laptop. And when it calls out to a peripheral, I can make it interactive. I can have it spit out something saying, hey, I wrote this to there. You've got to make sense of it. Or if it needs information, I can provide it. That's real-world, full-on emulation. Many people have done that. Anybody heard of QEMU? Or QEMU? Depends on which part of the country you come from, I think. So they do this very well. And actually, other tools have been built on QEMU to try to provide some hooks into the emulation process, much like what I find myself doing most of the time. And that is partial emulation. Or I'm sorry, that is pseudo emulation. Pseudo emulation, or what we'll talk about in a few minutes as a workspace emulator. I take the thing that I'm testing, disassembling, tearing apart, making sense of, like my Ada opening, but it's Vivisect, and I wrap an emulator around a function, for example. If I wrap an emulator around a function and I work and I have the emulator emulate through that function, I have a great deal of control, even so much as to do things that the system wouldn't do. Like, there's a great deal of value from emulating through every code block that a function offers and seeing what data is put into where. So I'm really ad hoc here, so please forgive me. If I see little dribbles of blood coming out your ear, I will try to ramp it back. So we've talked about real emulation. This is pseudo emulation, where I focus on a particular area, and then I hook in an analysis module, which we'll talk about in a little bit, and then I just say, hey, go run this function. Oh, by the way, I've got options here, like follow all the code paths, or at least all the code flow. So if I hit a conditional branch, what should happen, right? There's some flag that gets checked, and based on the value of that flag, one direction should be taken over another. Well, for some analyses, taking both makes a lot of sense. So we'll emulate along, we'll hit a conditional branch, and we'll say, we're going to go this way, but cue this one for later, we'll do more analysis. We take an emulator snapshot and store it. Then we take the branch, and we flow on through, and we're able to do things like track values through registers, or more importantly, see what gets done with them. So if I turn on a flag that says track all the reads, and then I kick off my run function analysis, it'll go through all of the paths, tracking all of the things, all the locations that are read from, and storing what opcode actually did the reading. More importantly for me, most often, I like to track writes. So I bring up my emulator, set it up for the function that I'm analyzing, and I'll say, emulate through this function. Allow emulation of the same instructions up to 5 times. What happens if I get into a loop? 5th time through, boom, that is done. And then that queue that I was talking about earlier, the next path is then analyzed. You're doing great. Where did the firmware come from? I could tell you, but I'd have to kill you.
Okay, that's what I'm wondering. Like, are you emulating in environments and then running information against that firmware?
So typically, what I find myself doing, the initial part of an assessment is go out and track down the firmware. If I pull it off of a device, that's one way. In a lot of ECUs in a car, we'll just give up the ghost if you know the magic things. Yeah. I'm often downloading it. A lot of vendors is like, hey, here's a firmware download. And that actually leads me to another point. With emulation, I don't need the full bootloader to do a lot of the things that I need. And so for some systems, we were able to download a chunk of the firmware, but the bootloader is not included in that. Partly because they never want to update it, because if you bork the bootloader, you kind of got to RMA it. As opposed to if you bork the current updates, the thing just doesn't work. It reboots into the bootloader again and says, okay, try again. But sometimes that bootloader has some code that can be interesting. So big, long conversation. So gather my thoughts here. So are you with me so far? Have I lost you? Should I go back and like sing a song? So somebody asked me about the bracelet earlier. Anybody else notice it? Anybody know what it is? Why I'm wearing a bracelet? Close, but no. So my daughter wanted to go down and hang out with her friends at a swing dancing extravaganza down here in GR. They get together once a week. So she allowed me to come along, and I had a lot of fun. And I recognized a couple of your faces there. You don't have to say anything, but Jim, you're amazing. This guy, ask him to dance later? Jeez Louise. Ladies. So emulation. So what I refer to emulation in these two categories. The real emulation we talked about, and workspace emulation. And the workspace emulation is the stuff that we've just been talking about, where we're able to change the way that the emulator actually works to get analysis fast. One of those things that we're able to track is if I track all the writes, when I'm done, I say, hey, max hit of 5 times. So any loop, I bounce through 5 times. I should have, if I see that I'm tracking 5 writes from the same address, from the same opcode, to incrementing addresses, what does that sound like to you? What's that? Writing an array, that's a good option. How about a libc function that does that exact same thing? It's called memcopy. Add in a couple other conditions, it's called strcpy. There are various things that we can tell by simply saying, okay, this little analysis monitor, and in this configuration, max loop, whatever, 5 times, go. And I do that for all the discovered functions in the system. And then I spit out all the ones that write to sequential data in a loop. Some of those are simply clearing space. That I will give you. So memset, basically. Although you'd be surprised how many functions, like in the Windows, in Win32 DLL, or user 32, kernel 32, there are an inordinate number of memory write loops that you might be able to use for your exploit. So this is all very interesting stuff that has been proven out to be very helpful. I cause hardware to do bad things. Let me take a sneak peek here. And I want to, before I go into the next thing I'm going to talk about, I want to make sure there's not stuff that I'm forgetting.
Manually using XRandR to set because there's two 1920 by 1080 resolutions, and I don't know what they are, and I tried switching between them.
One's interlaced. I have Wi-Fi turned off, or I did. Okay, so, okay. One thing that I was forgetting. So we end up, there was one last snippet of workspace emulation that I want to throw in there. I want the ability to say a memory dereference or something reading from memory. If that memory address doesn't exist, don't fail. So within the Workspace Emulator, there's a setting that I turn on that says, if I read somewhere that doesn't exist in my memory maps, return all A's. So if it's a 32-bit number, A, all capitals, you know the 4141 drill. It's amazing how easy that is to identify when you're walking through emulation analysis. They're walking off with my laptop. Okay, well, if you're in cahoots with him, I'm doubly scared, actually. I know where you live, David. So, hey! All right, here we go. We talked about this slide. Emulation is cool, right? That's the reason that we're here. Emulation enables behavioral analysis. Emulation monitors, we've talked about briefly. We'll talk about more. Partial emulation allows me to operate through snippets of code where the thing that I'm referencing may not have been initialized or exist. And yet I can survive and move on. Because oftentimes there are things where, heck, the emulator might not even have the instruction that needs to be emulated because of, new architecture changes. And yet it can survive to the next thing. Most often those things are not really pertinent for security analysis. Well, there we go. This is perfect. Okay, so example. I like hex. I like courier or monofont stuff in all of my talks. Have to have it. Even in my talks about how to create a good environment for cyber ninjas, I throw in some hex. I have to. So anybody can not read this? Okay. Okay, I'll make sure it's available. I know you'll get a copy. So we import, for this example, I go with the raw emulator, like the full-on, like no special frills whatsoever, the thing that I wrote for ARM. So I import the NV. NV is the name of the disassembly emulation framework within Vivisect. .arches, yes, arches has no E, don't ask. ARM, EMU for the emulator. I give it a name, EAAE, just because. I create an emulator by calling ARM emulator. I add a memory map at address 0 with memory permissions, read, write, execute. Give it a name, binary blob, and then I read in this binary thing. And that shoves all those bytes in at a memory map within the workspace at 0. Because this particular binary wants to be at 0. I set my program counter at 0. I can set my register. Now, there are several ways to set registers, but set register by name, because I want to give it a string, R0. If I said just set register and gave it a number 0 on this architecture, that would work anyway. And I fat-fingered that. That's supposed to say Atlas in late speak, but whatever. And then I get register by name, R0, and I print that in hex. I can then step instruction, and it executes the next instruction and increments the program counter. I get program counter. We're at 4. We were at 0. So super simple. I wanted to not make your brain hurt early on in the talk. If that's really cumbersome, and it is, because it's made for programmatic analysis, I wrote in Atlas Utils a little utility called runstep that basically tries to create a debugger type interface. So you see all the register values, and in this particular emulator, I've pre-seeded set values into the registers so that I know if they show up, because they're going to bring in values as arguments, right? So as arguments, if I see 41561001, then I know that that's going to be R0 plus 1 from the very start of the function. Blah, blah, blah. My program counter is 0. My current program state register. And then anything that is being accessed as an operand in the instruction, I just go grab that and spit out the contents. So in this case, it's a branch. It's not that helpful, but hey, you know, I didn't want to burn a lot of time on it. So this is an environment that I can very easily just hit enter and watch code execute. I can change values to make sure that the code flows in a certain way. This is very powerful for my interactive learning and getting to know. I'm more flirting with the code at this point. So here we're talking about the Workspace Emulator. Don't freak out. I just wanted to throw in the code that creates the base for the Workspace Emulator. Notice that the log write and the log read arguments are just part of the Workspace Emulator. These basically tell the emulator whether or not to store any reads and writes that happen during the emulation. So we store some stuff. We can hook things and wrap in Python code to emulate behavior. Uninitialized use. So the Workspace Emulator is really actually a workhorse. It wraps in a ton of stuff that you may or may not use, but it's really nice to have. Like uninitialized use. If I grab in an analysis, if I grab some register that's not been initialized, I want to know that. So we store stuff. We store a path. Now a path in Vivisect's emulation is actually an efficient way of storing, tracking information about the emulation through a function in a way that's like a tree. So you start at a root, and then as you branch off, it actually creates different branches into a tree of different possibilities. So you may say, at the end, you may have 5 different paths through a function, and you'll see that broken out into a tree if you visualize this path. I don't expect you to memorize that, but I want you to be aware of it because it may come into things later if I end up with time to talk about it. And then this right here, an emumon. This stores an emulator monitor that basically has the ability to create a pre-hook and a post-hook for execution. Before and after every opcode is executed, my monitor gets code execution with the current context so that it can say, hey, this actually is the thing I'm looking for right now. Boom, I can print it out, I can store it, whatever. Maybe I'm looking for hundreds or thousands, so I store it and I can analyze it later. I might not want to execute that opcode. So maybe there's something that I can do in the pre-hook. The post-hook can then check and say, hey, did I write right here? Let's go do some preliminary analysis. So we've talked about the analysis module class a little bit. Talked about the run function class. Run function has a number of arguments that you can use, but the ones you want to be aware of is the max hit, so that it can follow through loops and not just go on forever. You've heard of the halting principle, right? The halting problem. Path tracking, we talked about that, and read-write logging. Apparently I threw this in here to remind myself that I wanted to talk about these things. The one thing we haven't talked about is emulation snapshots, and I'll tell you about that in a second. So, a couple applications of emulation that are already in use today within Vivisect. There's a function emulate to here, and you see this on the next slide. Then calling convention analysis. Who knows what a calling convention is? Okay, about a quarter of you. Because compilers need to allow you to write code that leverages other code bases, those other code bases, known as libraries, create functions that adhere to some particular way of handing in arguments and returning values, and a couple other things, but that's basically what it is. It's a contract saying if I'm using libc memcopy, I know that that has this particular way that it wants me to hand in arguments, and it will return a value in this particular way. So the calling code, the compiler, can make that thing work well with the library. So it turns out reverse engineering benefits greatly from being able to automatically spit out, hey, this has this many arguments, and it returns an integer. Emulation.py is also basically some of the same analysis stuff for different architectures. Is possibly code, that's something within the core functionality of Vivisect, and then emucode is also another module. So show emulator state, or emulate to here, when you're looking at a function in the Vivisect window. You right-click on the function itself, or actually anything in the function. Sorry. You right-click on the address location of an opcode that you're interested in. You go down to the function menu, and you choose Show Emulator State. Now what happens is very rapidly, a lightweight emulator is cranked up, a workspace emulator, and code path is found from the start to there, and the values in the operands are then displayed to you, shown right here. So we run an emulator down to 32 DOE, and stack delta 0. We've not actually changed the stack at all. Here's the opcode there. R2 comes in having this value. Well, that was put in by two different instructions here: move wide and move top. These are ARM instructions that are used to populate a 32-bit value within a register, because ARM instructions are all how big? 32 bits, or in a lot of cases for thumb mode, 16 bits. So how do you load in a 32-bit number into a register if you've only got 32 bits to work with in the first place? This is how. So this actually throws off a lot of disassembler static analysis tools, because this is an address for this chip that I'm looking at. This is an address into RAM. But it looks like EOC and 801 are the two numbers that I'm looking at. Turns out I'm actually looking at 801 OEOC as an address, and since it's a dereference, it says the dereference of R2 is actually a dereference of this, and that is unknown because we don't have that memory mapped into the emulator. Here's the calling convention example I wanted to show you. Here's a function. It's a System 5 AMD 64 call, which basically everything on POSIX in 64-bit mode has this calling convention. So I don't really have to work hard to figure out that part. But it returns an integer, and it has these arguments handed into it. 1, 2, 3, 4, 5, in these particular registers in that order. Furthermore, going through all of the emulation of the function, the emulator analysis tool found all of these local stack variables referenced throughout the code. Well, there's some interesting code that makes all that happen. I won't go through too much of it. I don't want to make your ears bleed, and we're running low on time. But notice at the top, this is actually a very common thing for a Vivisect analysis module. There's a function called analyze function. It receives in a Vivisect workspace and the function virtual address, the function address. We immediately tell the Vivisect workspace to give me an emulator. This is going to return a workspace emulator for that particular architecture. We create an analysis module, which we'll talk about here on another slide for this particular one. We snap that in as the emulation monitor using set emulation monitor. And then we call run function, max hit 1. All I want is code coverage. Does this make sense when I say code coverage? I could do it like this and like Ada words. We then say, hey, do I have an API already defined for this function? If not, build it. Build function API, and it hands in the emulator and the emulation module or monitor, and build function API does all the real heavy lifting of analysis. We then set up the API, do some stuff, get the stack offset, and then we create all the information about the arguments and the local registers, yada yada. Then we add in the analysis results. What's that? Right here. I couldn't fit it on that slide, so I referred to it later. I'm glad you're following along. So build function API, what the hell is that? Turns out it's a function. Actually defined in calling.py. It's not just an intrinsic thing. And it does all the heavy lifting. Again, I won't go through all this, but I do want to say the emulation monitor just keeps track of all of the maximum stack offset that has been that's been found during an emulation run. So the max stack offset, and we divide that by 4 in this 32-bit case, and that's the argument count. If the argument count, this is for i386 32-bit, just so you know, there's a few things that are kind of assumed here. We start off with cdecl. See, this is that dozen calling conventions. We start off with cdecl because why not? Very likely it's going to be cdecl unless we can prove otherwise. If it returns bytes, meaning at the very end of the function, when it hits, when it does the return, if it returns like 8, ret 8, anybody know that one? On Intel architecture, ret 8 says, well, return down here to this place, but then knock off 8 bytes off the stack, which is called callee cleanup. The guy who got called cleans up the call stack. So if that's found to be non-none, then we know it's standard call. cdecl doesn't do that. Blah, 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 stack index. Undefined keys. This is really cool. The emulator, as I said before, tracks uninitialized accesses of stuff. So in the next slide, which this function was too big for me to actually have you see it and fit it all on the slide. So this is that reference point. This is not the second time. This is like the pivotal point. So then we walk through the undefined keys, and we try to figure out just how many of the actual things that are used for that calling convention arguments are used, so that we know if we hit one that's not been had uninitialized use, that's the end of our arguments. We've got like 4 or whatever it is. Wait, did I hit back? Okay, analysis monitor. This is the guy that gets created and plugged in. It's pretty simple, really. It subclasses Vivisect EMU monitor, analysis monitor. We give it a setup, a constructor, and then if we define prehook, then that prehook gets called before every instruction. In this case, we just look to see if the op is in what's called the bad ops list. So we go through and we identify a bunch of things that really just should never happen, like instructions that decode from all zeros or all F. And that's in this list. So if the opcode is in that list, then we just stop. There's an exception there that says this can't be. We're done. Otherwise, we call the parents prehook, and then we check. This is that bit. If it's a return and it's got an operand, then grab that operand. It's got an immediate value, and we'll store that because that's important information for the standard call. No, I did not mean for you to become great experts at calling conventions here. I just wanted to give you some pragmatic examples of how emulation is already in use. For AMD64, I cut out a ton of stuff, but for if the calling convention is System 5 AMD64 call, which is really easy, it just says if it was brought in from an ELF file, that's the default calling convention. If the emumon stack max is greater than 0, go through and just dig through how many arguments we've run into. If we've got like 40 arguments, bail, something's wrong. And then we set up the API. Another use that I actually like a lot, pointer analysis. When running a Vivisect analysis pass, at the very end of everything, when you've taken all of your entry points and you've disassembled them and stored information about them, then any pointer that we can find in memory that's not defined and doesn't have something known about it gets run through this function, analyze pointer. We see, first of all, hey, if there's already a location, if we've analyzed that location already, get out. Otherwise, is it probably a string? If so, hey, make it a string. Is it probably Unicode? If so, cool, make it Unicode. Is it probably code? Gee, where's his probably code, Paul? On the next slide is probably code. So we go a little deeper. Hey, is this executable? Because if this isn't executable, then, screw it. If it has a function signature, because it turns out compilers like to use pretty similar types of bytes that start out every function, called a function prologue. If it fits into a function signature, then cool. If we've already analyzed for whether it's code, then bail, because it obviously isn't, because it's not been defined. All right, now, once we've gotten all that crap out of the way, that's just administrative garbage. The next thing is, give me an emulator. Slap in this watcher emulation monitor. Run function, max hit 1. If it makes it through without bailing, like, bad op, or, memory, or just like undefined, or something bad happens, then it's clearly not code. If it gets all the way through and it looks good, then return true. It's probably code. Watchers mentioned, no time for it. Go check it out. We can also look at, wait, what? Damn it. I got ahead of myself. I get these two confused. So that was one thing for following pointers. This is another one that runs at the end of code that looks at anything that we've identified as a pointer. Do the exact same thing. Is it executable? Have we tried it already? Get an emulator, slap in watcher, run function, see if it's good. A word about snapshots. I have a couple minutes, but not much. One of the cool things about an emulator for this type of work is that I can emulate through to a particular point in emulation. Maybe the point that allows an attacker to provide an input. I can save a snapshot of it. I can provide inputs to it and allow emulation to go. And after some predetermined blah trigger, I can say, forget it, it didn't work. Snap back, just slam the original context into the emulator and go again. So emulation fuzzing. So here I get a snapshot of an emulator, and an emulator is just a register values memory tuple. Okay, so it takes basically all the stuff that makes up the emulator, offers it up, and then there's another one called set emu snap that you'll see in a second. So I just wanted to show you the registers. This is that register that we just set earlier to 47A45, and a bunch of zeros. Here's our 4 because we executed that one opcode. If I set the 0 register, which is R0 on ARM, to 1337 hex, and then I slam that snapshot back into the emulator. Basically just get rid of everything and put this back into memory. And then I get register 0. It returns the original value, not the one that I set. No GDB? No problem. This is just a copy of the other picture. Rob gadgets. We don't have time to talk through a decent analysis of Rob gadgets, and I actually, honestly, would get shot if I told you a lot of the things that I can do with emulation and Rob gadgets, but here's some things to tickle your brain. A monitor or code that watches for op is return. Start at 0. Don't necessarily go to a return instruction, because sometimes on different architectures that can look very different. And sometimes, yeah, anyway, whatever. Start at 0, increment by 1. Go for a set amount of instructions, and then bail. If I haven't gotten to a return, bail. If I get to a return before then, now we do some analysis. Things like, does the stack pointer now hold the value of some other register? That's very interesting information. Is R4 one less? Turns out increment and decrement is actually a very powerful ROP gadget. Have we written the value in R5 into the location pointed to by R4? This is called a magic write. R5 and R6, are they loaded from the stack? That's super powerful, especially if R5 and R6 are really the parts of the magic write. I found this once in a version of Firefox. It was beautiful. It's like I had arbitrary read-write. All I needed was just to fill up the stack with what, where. It was amazing. It's real. The next part, though, is you got to look for the bad stuff. If you write to some clobbering place in memory or a place that doesn't exist, okay, that's kind of a problem. No. I love symbolics. I have, in recent years, come to recognize that symbolic analysis and graph theory is a super powerful form of analysis. But emulation still is very powerful, and they solve different problems, and to have both capabilities is super powerful. Here, bug hunters, welcome. There's always cool stuff to be done on Vivisect, and new architectures to implement, bugs to squish, functionality to add. We welcome some eyes. And then I included a little cheat sheet, how to get involved with interactive Vivisect. Get into Python, import Vivisect, create a workspace by saying vivisect.vivworkspace. And then either, if I already have a Vivisect workspace created, VW, load workspace, and then I give it a name. If not, load from file, and I give it a file name of the thing that I want to go analyze. I kick off an analysis pass by calling analyze. And at the end, I save workspace. I do this actually on either one if I do any changes to it. That's it. If you want to get in and play with the emulator, start off with that. Use the Vivisect workspace, get emulator. Get memory maps. This is a cool way to show you the memory maps in the memory subsystem. We can add memory maps. We can parse opcodes and actually get a Vivisect opcode object back. We can step through one instruction or run an entire function. We can set the program counter, and getting is the same thing without the program counter argument. We can set a register by name or get it without this val argument. We're going to read memory, given an address, and then just the number of bytes. We can write memory. I didn't include that in there, but write memory is very similar. Read mem value. If we know we want a 32-bit integer, we just hand this address in with a number 4 for 4 bytes, not bits. And help EMU. Very helpful. Vivisect has a integrated server component that allows for collaborative disassembly, emulation, tooling, whatever. What I'll often do is I'll have the GUI up against a server that hosts the Vivisect workspace, and then my command line tool also connects to the same server, same workspace, and then what I do on the command line gets kicked into the GUI easily. Now I can do it in the GUI, but it's not IPython. So in conclusion, interactive Python static analysis, emulation, and symbolics. I love it all. Go play, go and do great things. Pass on what you have learned. And then I left some crap at the end. So, yeah, I won't tell you. Anyway, thank you very much. Any questions?